This is a graph theory example that we're going to look at Eulerian paths, Eulerian circuits, and traversable circuits, traversable graphs. Draw the graph K25 and K44. So these are bipartite complete graphs. Draw these graphs out and name the vertices. So just as a sort of quick remark, K integer integer, that's a bipartite complete graph. So there's two sets of vertices, and pick a member of one set of vertices. They're connected by an edge to each and every vertex of the other set. That's the idea of a bipartite complete graph. Let's draw K2, 5. So let's the first set, we'll have these vertices up here, and let's connect them to this set down here. We'll name them. Let's call this 1, vertex 2, vertex 3, vertex 4, vertex 5, vertex 6, and vertex 7. So, and they have two sets. So this is set 1, this is the set of 2 over here, and this is the set of 5. So 1 is connected to everything in the other set of vertices. Okay. And likewise 2 is connected to them all. Let's do that for K44. It's pretty similar. Name them. Let's call this 1, 2, 3, 4. That's the first set. And 5, 6, 7, 8. That's the second set. And again, just connect them up. The vertices are not connected to other vertices of their own set. So 1 won't be connected to 2, 3, or 4. Right, like that. Just 5, 6, 7, and 8. Now, it's a bit hard to read here, and there's quite a lot of edges in this, so I'm just going to be mindful of that when we are doing future questions. There's quite a lot of edges there. Now, give the adjacency matrix of K2 and 5. I'm going to skip that question because the adjacency matrix stuff is straightforward enough, and just for the sake of brevity, I have other YouTube videos for it. Now, which of the two graphs, one, neither, both, specify which one, are traversable? So, a traversable graph. A traversable graph contains an Eulerian path. Now, the definitions of Eulerian paths, Eulerian trails, and so on vary from book to book. Now, so what I recommend is just sort of checking out your textbook or whatever, just to make sure that you're using the same terminology I am. I understand an Eulerian path to be as follows. What I'm going to do is actually take this off. I'm going to do it for K2 and 5 here. So I'm going to go back here. And what I'm going to do is actually get rid of a couple of these edges. I'm going to draw them in again. So I'm just going to sort of rub them out here and just leave the vertices. And the reason for that is so it just makes a bit clearer what I'm doing as I go along. So we're looking at traversable paths, or graphs. Now, a traversable graph is a graph that has an Eulerian path. Okay, so what is an Eulerian path? An Eulerian path is that we can visit all of the vertices using each edge exactly once. So I have to draw out my graph again, but this time I'm not going to take my pen off off the page. I have to draw out my K25 graph again, but without taking off the pen. So the pen can't leave. I have to do it all in one fell swoop. And also I have to visit each of the vertices, and I have to sort of have all of the edges I am supposed to have. So a trick there would be sort of to say that the degree of each of these ones down the bottom should be 2, 2, 2, and 2, and these should all have degree 5 up here. Okay, so let's do this. So let's start at 1, go to 3. Where can we go with that? We can only go to 2, because now 3 has a degree of 2. Let's go from 2 down to 4, because we can't go to 1. Okay, so 4 is just as good as any. 4 and 1 have to be connected up. There we go. Let's go from 1 to 5. There we go. Now I've sort of inadvertently taken the pen off, but I think you get the idea. So we're going to sort of go here. Now, there, we've visited all of the vertices. We have all the edges that we are supposed to have. And there we have a traversable graph. So it was traversable, but I just draw your attention to the fact that I started at 1 here and finished at 2. So it was a traversable graph. This is my starting point, and vertex 2 is my finishing point. So it's a traversable path, but I did not finish at the same place. That is the definition of an Eulerian circuit. Oops. That's my eraser there. An Eulerian circuit is an Eulerian path with the same start and end point. So it's a traversable graph, but it's not an Eulerian graph because I did not end up back at 1. Therefore, it did not contain an Eulerian circuit. I did not end up at my starting point, which is 1. So therefore, it doesn't contain an Eulerian circuit. Therefore, the graph is not Eulerian. Okay? So, no Eulerian circuit. There's an Eulerian path, no Eulerian circuit. For K25. What we're going to do is actually do out the same thing again here. And again, I'm going to just erase these temporarily so that we're not drawing everything out from scratch. Essentially, what I have to do is be able to demonstrate that I can draw visit all of the paths, all of the vertices, and put in back all of those edges back in. Also, what I'm interested in is, do I end up at my starting point that I'm supposed to start at? And just clean this up a bit. So it's an Eulerian path, but also is it an Eulerian circuit? So do I end up back at 1? Okay, so let's start off 1 to 5. Okay, 5 to 2. 2 to 6, 3 to, there we go. I'm just sort of starting out just to get it going. Now, I'm looking for somewhere I can go. I'm at vertex 5 and I have connected to 1, 2, and 3 now. So this is where it gets a bit more interesting. I can go to vertex 4. Okay. Now I'm at vertex 4 and it already has degree 3, but you notice that it's not connected to degrees vertex 6. Okay. Vertex 6 is connected to 2, 3, and 4, but it's not connected to 1. Okay, so far 1 is only connected, oh sorry, is only connected to 5 and 6. It's not connected to 4. So that's me trying to not move my pen. So I'm down at 7 now. And 7 is not connected to 2, so connected to 2. 2 is not connected to 8, so let's connect it to 8. So I'm down at 8. What is the only one? It's probably a bit hard to tell here, but what is the only point that vertex that 8 is not connected to? And it is 1. Okay. Now, so very bad, very stringy example, but what we've done there is shown that K44 is traversable, but it's also Eulerian because I ended up back at the same point. Now, you probably might do this with a ruler, might help, and also use a much bigger page. So it is traversable. It has an Eulerian path, and that Eulerian path has the same beginning and end point, so it's an Eulerian circuit, so it's traversable and Eulerian. So that ends this presentation.